Hello everyone. This video is about common emitter amplifier with emitter degeneration. In the previous chapters, we talk about common emitter amplifier, and this is the circuit for the common emitter amplifier. When I say with emitter degeneration, this means the tail of the transistor here has a resistance. And I can tell you, by adding the resistor here, the circuits will undergo a very substantial change. It's not a trivial change. So this is not going to be common emitter amplifier anymore. It is common emitter amplifier with emitter degeneration. And to resolve the circuits, we again need to use the pi model or whatever model you have. And to start with, we need to do this. So the transistor will be replaced with a pi model first, and we also need to account for the early effect. And the output to C, D, and B. So this is the pi model for the bipolar junction transistor. And like what we did before, we are going to short circuit the VCC here. So if we do that, then what we are going to get is we have a resistance here. And RC and no. And this one is going to be connected through a resistor to ground. So it's not a trivial change. By adding a little resistor here, the whole circuit undergoes a very substantial change. So now the input will be tapped here, and we have a resistance at the input, and it is going to be R1 in parallel with R2. And in. So this is the small signal representing this amplifier. This amplifier is so-called common emitter with emitter degeneration. And to solve this circuit, we have to be very careful, because V pi is not going to be V in. So what should we do? My suggestion here is we temporarily name this node Vx, and the current IB is substantially smaller than IE. IE is much larger, okay? IE, and also is much larger than, is much, sorry, IB should be substantially smaller than IE, and also is substantially smaller than IC. So this is the number one fact. We are going to establish this fact before going forward. Let's yeah, we are going to continue. Because the current IB is too small, we can, for the purpose of analysis, we can ignore it. So for the time being, right, we can temporarily ignore it. And we use our analysis to work out this network first. So what is this network? This network contains output together with a parallel combination of analog and the current source. This is the dependent current source, and subsequently it go down to RE. So the important assumption we have here is IC and IE is substantially larger than IB. And IE and IC are similar in value. And another thing that we need to know is, what is V pi? V pi according to here, it is equals to V in is equals to this voltage. This voltage is V pi. So V pi plus Vx. And what is Vx? Vx according to here, it is IE times RE. And because of the fact that IE is almost the same as IC, we can say this. And now the problem now is IC. What is IC? We can work out IC just based on the output level here. VL divided by RC is the current going downward. So IC is going to be minus VL divided by RC. Okay? So based on this assumption, we can quickly find out V pi is equal to V in plus RC and RE. Now, the next step that we are going to do is to simplify this network. And we have a parallel combination here. We can convert them into a testing equivalence. And the way how we do it is, First, we have a network. IE, and this is BX. And then we assume IE is almost the same as IC. And we are going to do the conversion on the fly. This one and this one, you will end up with a battery, the voltage source equals to Gm V pi and analog. And later, you have a resistance, analog here. And then the current here will be IC. And this is just an approximation. With this approximation, we have ignored the base network. Now, it's now getting more downhill now. And we know that the output voltage, the circuits here can be resolved using Kirchhoff's voltage law. By Kirchhoff's voltage law, V now is equal to IC times this resistance and times this resistance. Plus Gm V pi and R0. And previously we have found out IC here is equal to minus V out divided by RC. Okay, so we can just simply substitute to here. Minus V out over RC. And now something tricky is here. We need to know V pi, and fortunately we have the expression for V pi here. So we are going to substitute this here. Plus V out and RE divided by RC. We need to do algebraic manipulation, unfortunately. But it's not difficult. What we need to do is to combine the terms with V out. So we do that. V out. This is 1. And this term will be R0 plus RE divided by RC. So this one has gone to the left side, and this one Tougher, GM, R log, and then the trunk expression, RE, and then divided by RC. On the left side, on the right side, it is going to be easy. And now we are going to continue, and we are going to erase this circuit to free up some space. What we need to do is to simplify this expression. We know, better minimize the usual. We know, in this case, it is times 1, and we are going to do this, right? R log plus RE and plus GM R log and RE and divided by RC. And the left side is single. GM R log V in the left side. And now we need to simplify the expression here. We need to simplify this. Now, to do that, let's try out here, R log RE, and see what it gets. And if we take RE out, we got 1 over GM R log. And previously, we have known that this term GM times R log is much greater than 1. So in this expression, we can safely assume this one is equal to RE GM R log. So with this in mind, the expression here can be simplified enormously. And we are going to do it now. No. 1, and then R log 1 plus GM RE, and then RC. So we can simplify the circuit now. What we need to do is we can extract the voltage gain from this expression here. So the right side of the equation and R log, and we have this one, yeah, RC plus R log RE, and this RC is going to be here. Now, there's a trick to further simplify this expression. What we need to do is to multiply the top and bottom with 1 over GM RE. And if you do that, Then if you take a look in this expression here, this one is, sorry, I should say, right? If you take a look in this expression here, this one is actually a parallel combination of R0 and this one. So eventually, what you are going to get is a much simpler expression at the end. It is going to be GM divided by 1 plus GM RE. And then this one is going to be R0 in parallel with RC. So the final expression is surprisingly simple. This is the voltage gain. And you know that the net effect of this expression, let me see. Yeah, this is wrong. R naught and RC. So compared to the common emitter amplifier without any emitter degeneration, and we noticed that the voltage, the voltage gain here is the equivalent expression. This expression is somewhat like the transconductance. By the way, there should be a minus sign here. I don't know why I don't have the minus sign. Minus. The that's very good one. It should be minus. And this one is minus. And this one is minus. Okay, that's much better now. And this one is minus. Minus. And this one is minus. Yeah, we correct it immediately. Yeah? And this one is minus. And this one is also minus. Okay, now it's better now. So essentially, the resistance at the output has got modified. Normally, in the previous chapter, the voltage gain for the CE is for CE amplifier. VR over VE is equals to minus GM, and then the parallel between RC and R0. This is what we get from the previous chapter. But now there are a few things we need to learn. First, the transconductance here. The transconductance is the current produced as a result of the input voltage change. And we know that the transconductance here is scaled down by 1 over 1 plus Gn times Rz. The early effect resistance here is scaled up by 1 plus Gm times Rz. So this is the point we need to learn. Uh, um, and now, what about the input resistance? And we are going to work this out, input resistance. And if you look at this voltage instead of this one, we can find out uh, the input resistance. So the next step is to look at the input resistance. RE in this case is equal to R1 parallel with R2. And uh, what about the network here? We have an input, we in, and we have a resistor R1 plus in parallel with R2, and we have a R pi, and we have another network, the network here, and R pi, the current in R pi is IB, but the current in the bottom resistor is IE. We know that IE, yes, let's say this voltage, this one is Vx. Vx is equal to IE times RE. Yeah? There's no problem with that. But also, uh, this one is equals to uh, 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 1 plus beta IB times RE. So, do you agree that we can use the uh, algebraic trick here to rewrite the circuit? In this case, Vx is equals to IB times this much resistance. So why don't we just convert this into this equation? This one is difficult to handle because you have IB here and the current here is different. What we can do is we convert it. And the resistance is 1 plus beta times RE. So with this in mind, what we can do is RE by looking at here is equal to the parallel equivalence of this resistor and this one. And what is this one? R pi plus this one here. So we found out the input resistance is not as simple as we think. It is something like this. But now we can still further modify this. What we can do is, we know R pi is equal to what? R pi is equal to beta divided by Gm. And this one is almost the same as beta. So you can just simplify the circuit on the fly. And beta So this is what you can do. And if the resistance here is large enough, this is B terminal, right? Okay. Let's leave it up. If the resistance here is large enough, if RE is large enough, such that GM RE is substantially larger than 1. So we can say this, right? R in is equals to R1, R2, and then we can beta and then RE. So this is the one of the way to simplify it. But we don't really need this assumption. All we need to know is the input resistance can be written in this manner. So we know that the voltage gain have in the expression in the formula for the voltage gain, the conductance gets scaled down by this amount. On the other hand, R log is scaled up by this amount, and the input resistance is also scaled up by this amount. So there are a few things we can tell to the world. The first thing that we know is the uh, the input transconductance is scaled down. By the factor 1 over GM. The input resistance originally in the ordinary common emitter amplifier, the input resistance is R pi, but now you scale it up by 1 plus GM times RE is scale up by 1 plus GM RE. Sorry. And another fact that we should look at. Now we still have a little bit space here. The early effect is also scale up. Early resistance. I don't know. Is scale up. By 1 plus GM RE. So all these are important information. And we have looked at the voltage gain, we have looked at the output resistance, sorry, input resistance. And what we have not known is the current gain. And we can use the same method to work out the current gain as long as the input voltage, the voltage gain is known. So what we can do is Uh, we can continue. So this is another heading on current gain. And the current gain where I out is equal to IC minus IC precisely. Uh, so it is V naught divided by RC. And against the input voltage is the input voltage divided by RE is the input current. And now the input voltage and the input resistance, yeah, it is here. R1, R2, and it is, we better use uh, the Excel expression. So the current gain is equal to this one and this one. E naught divided by RC and the E divided by this tranche of expression. And we know that the voltage gain is can be calculated from here. So we can do that. Gm over 1 plus Re. This is the voltage gain and times and then times another value, right? So this is the final expression for the current gain. I hope it is clear enough to you. It's a bit confusing at the end of the lectures, but this is okay. If nothing is wrong. So this is the expression we have learned for the current gain. So, and this one is the voltage gain. And this one is the input voltage, the input resistance. If you have any question, please leave your questions to the comments box. In the next video, I will teach you how to use T model to resolve this problem. T model will be much easier to work with. Before doing this, please remember how the formula looks like. Okay? Thank you.